So, 1985, Carl Sagan wrote a book about a woman who does what I do. And it's been a lot of fun ever since then. I'm delighted to be here in this venue where I can see you. Often when you're interacting with an audience, there's this big blinding light in your eyes and you all are in the dark. But I'm really looking forward to the opportunity to have an interactive discussion tonight. And I'll tell you some of the things that are particularly important to me about this film. It's hard to do a stand-up comedy about the terrible science in the movie because there isn't much. It's actually extraordinarily well done. But there are a few things that didn't quite go right, and we'll talk about that. And if we have time at the end, I'll go on about some of the things that Carl Sagan was very adamant about including themes in the movie, and that actually make it more real for those of us who have the privilege of working in the scientific environment. So now we're going to start with the opening scene, which has won numerous awards. And I remind you, this movie was 1997, predated all the fabulous CGI we have now. So this is the longest digitally animated, continuous shot film piece that had ever been done. It does have a few problems, but let's take a look at it. Pretty nice cinematic transportation at the end. All right, that was a fantastic scene. That's absolutely beautiful. And it did a really good job. It gave the audience time to absorb the lesson that as you go farther out in space, you're going farther away in time. As you pulled out, you were hearing radio broadcasts from longer and longer and longer ago. So that's the right idea. Got that right. But radio waves, electromagnetic radiation, travel at the speed of light. Just takes a bit over 6 hours for a radio wave to get out to the edge of the solar system. And yet by the time you were going past Jupiter, you were listening to stuff from the 60s, right? This is a film in 1997. It's supposed to be real time. And so the problem with the physics there is that the radio waves are moving at the wrong speed. And it makes sense cinematically to do this, because if you get to the edge of the solar system and you're only listening to things that are 6 hours earlier in 1997, it's going to be really hard to tell this story, right? But it does a great job. It goes out and then it goes radio quiet because the radiation that we broadcast hasn't had a chance to get there yet. So that was all great. Little tiny quibbles. I think the Nixon "I am not a crook" speech is out of order chronologically. But it is great. So a very wonderful, wonderful way to inform the audience of a physical principle without lecturing them. So were any of you confused by that when you saw it in the theaters? Did you all get it? Yep. Do you have any questions about it now? All right. So why don't we go on to the next? Okay, great. Let's see if I can stop that.
I guess my question is, if there were a planet that were not too far away from us, and we could observe the radio signals from it, and let's say they were producing the same kind of signals that we produce for radio and television and that, would they be coherent enough for us to turn them into voices and pictures, or would they be all scrambled up?
It's actually not so much a question of the scrambling, because you can, if you can in fact receive the signal with enough signal to noise, and you knew the decoding, you could unscramble it. It's more a question of power. So let's put a TV transmitter on the nearest star system, 4.4 light years away, the Centauri system. With the telescopes that we have, that we're using today, there's not a prayer of us having enough sensitivity to detect that leakage radiation. But, so that's our most prevalent kind of leakage. But now let's take the strongest transmitter on the planet. Right, that's a radar associated with the very large telescope in Arecibo, Puerto Rico, that 300 foot diameter dish in a sinkhole in the limestone karst of Puerto Rico. Our biggest dish, a transmitter that's got megawatts of power, put 10 to the 7 more gain on it with the dish, focus that out. If that were being sent towards us, we have the sensitivity to detect that halfway to the center of the galaxy, right? So our television and radio broadcasts are intended to illuminate an audience in the next county, not the next star system. But the planetary radar is used to map asteroids, right? It's used to show us the fine detail on these bodies between the orbits of Jupiter and Mars. So there's some heft in that. That signal is pretty detectable. Actually, we didn't ask the overflow room if there are any questions over there. Hearing no voice from the sky. Oh, okay, another question here. Yes, please do that.
We've got a question up there, actually.
Oh, that's up in the dark. Okay. So where is the question?
It's right here. If, in fact, the first radio signals went out in the early 20s, where are they at now?
Can
in
you do
diameter?
Okay. 1920. This is 2015. So we did that calculation before dinner. That's 85 years, right? 95 years. We did that at dinner. It's 95 years. So that signal is 95 light years out. That means there are many thousands of stars that could have detected the signal. Unless they're closer than half that distance in light years, there wouldn't have been enough time for someone to detect the signal, turn it around, and beam it back to us, and for us to have received it today. So the radiosphere is this expanding bubble of our transmitted information, and that's out 95 light years and moving 1 light year per year and getting fainter all the time. So they're going to have a pretty big antenna to pick up those weak signals. So this one here.
Is this working?
Yeah.
The opening scene ended with the girl on a ham radio. Were you a ham radio person at that age, approximately?
I actually never got a ham radio license, although I did play around. You have to learn Morse code to get your license. I did play around with that. I used to take radios apart. That was what I did. And then it would be, get it back together. There'd be this extra part. And there'd be, Dad! Right? And he'd say, take it apart and figure out where it goes. So I did love to destroy radios. Okay, we finished with questions on the opening scene, which is absolutely, it deserved every award that it got. But they really did have to take some artistic license with the speed of light. So now let's go on to something that chafes me every time I see it. If I had left Arecibo 1 day later, I probably could have prevented this. So here it goes. It's an awful waste of space. is the way that ends. A phrase that gets used number of times. So did you get it? All right. Jodie Foster took a number, 400 billion, 4 times 10 to the 11 in scientific notation. She divided it by 1,000,000 and by 1,000,000 and by 1,000,000 again, and came up with an answer that was 1,000,000. Well, 10 to the 11 times 10 to the minus 18 is 13 orders of magnitude smaller than 10 to the 6th, her answer. So it was really frustrating because this particular clip was the one that Warner Brothers was willing to share with Ann Druyan to show to a group of scientists and engineers at the Jet Propulsion Laboratory when they had a memorial service for Carl. And after this scene, you just heard this collective intake of breath. It was very, very frustrating. There was a reception afterwards. Jodie was there. Some of the cast were there. I said, Jodie, it's wrong. You got to change it. It's all wrong. And she said, oh, it can't be wrong. Let me get the screenwriter. She brings over this kid all dressed in black, Hollywood guy. Oh, he says, I worked so hard on that. I was so sure I got it right. And you say, dude, all you had to do is ask. And apparently, Carl had found this mistake twice in the script, but it never got corrected. And so I'm ranting and raving and saying, oh, you got to change, you got to change. And so they bring over the Starkey, the executive producer, and yeah, he said, well, it's okay, we'll loop it. Meaning they'd re-record it saying like maybe 1 in 1,000 rather than 1 in 1,000,000. But it's such a close facial shot, they couldn't do it. And then they said, oh, well, we'll change it before it goes out on tape and video. And it's never gotten changed. And then the really galling thing is, Starkey says to me, well, Dr. Tartar, how many people do you think are going to get that? But that's damning. That's awful. That means that we teach our students and we teach our population mathematics so poorly that they don't have the ability to think about big numbers in a meaningful way. And, these are the people that are going to end up deciding what happens with billions of dollars as politicians and lawyers in the future. So this one really chafes. Okay? All right. So any questions? Does it bother you now that I've showed you? Did anybody get this when you were watching it? Be honest. Did anybody get that? I see a few hands. Good. All right.
I was able to enjoy this scene. Is the microphone nearby?
Yeah.
I took it a different way. Maybe people would find it interesting.
You have a new math?
No. No, same old math. Just love movies, and I guess I always try to find good in them. The way I took it to mean, yeah, I did the math correctly, and when she got down to millions of civilizations to communicate with, I said, oh, well, she used the 400 billion stars of our galaxy as merely an example, and she was referring to millions of civilizations in the entire universe. And so I just let that one slip by. I guess I gave him credit.
Number of stars in the observable universe is not 10 to the 11, which is the number of stars in our galaxy, but it's 10 to the 22. There are 100 billion galaxies in the observable universe. 10 to the 22 times 10 to the minus 18 is still not equal to 10 to the 6th.
You're right. They haven't counted every star.
Anyway, good try. She would have been... Yeah, she would have been closer. I would, that paper would have gotten a D rather than an F. All right. So, anything from the overflow room? We have anybody else who wants to help with remedial math? I mean, that one is my all-time problem with this movie. Okay, moving on. RFI, radio frequency interference. What don't you do when you detect a signal? Okay. What don't you do when you detect a signal in the middle of a radio telescope array? You don't pick up a transmitter and start transmitting, because that transmitter in your hand is so much stronger than a cosmic signal. You totally saturate your receivers. Now, that's a VLA walkie-talkie. You saw the NRAO logo on it. They're used mainly during maintenance. They actually operate at frequencies for which there is supposed to be no sensitivity in the receivers, but there is sensitivity at the intermediate frequency, the mixing products. So those receivers aren't used during observations. So, I mean, the idea that you would start yelling at your colleagues, right, and broadcasting is so extreme. Let me give you an example. We all carry around these wonderful smartphones, right? Even a dumb phone. It's got a transmitter in there, transmits about 1 watt of power. If you took a single cell phone and stuck it on the moon, if you could do that trick, that cell phone at the frequency that it radiates, and it could be one of a few, because there will be the second loudest radio source on the sky. Cosmic signals are really, really, really weak. And so at a radio observatory, we go to great pains to try and exclude our own transmissions. Some radio observatories allow only diesel cars on the facility, because the sparks in a normal ignition system, in fact, create a lot of broadband noise, like lightning, and that can interfere with the reception. So that's kind of a boo-boo. Anybody think about that when you saw the movie? No. Okay, you did. Do you have a question?
Yes.
All right. There's a question down here.
With the strength that you mentioned of the cell phone signal, am I correct that at the VLA they don't really discourage cell phone use of any kind while you're there? Correct?
Yes. And at the Allen Telescope Array, you come through the gate, big, turn your cell phone off, right? And we actually restrict. We do a lot of work with outreach, and so we restrict camera crews to Tuesdays when we have maintenance, simply because of the transmitters that they use, their microphones, their wireless stuff. It's amazingly awful. So yeah, you come to Hat Creek, and you're going to have turned it off anyway, probably, because it won't work. At our observatory anyway. It's out in the boondocks. There aren't any cell towers. Nevertheless, if you don't turn it off, what does your cell phone do? It's trying to call home. It can't raise a tower. So it increases the power and tries to call home again. Right? So when you visit a radio telescope, please turn off your cell phones, the Wi-Fi on your computers, all of that stuff. Turn off your electronic equipment. Yes, question here. All right.
You mentioned that if you had a cell phone on the moon and you transmitted it, it was the second most powerful source. What is the first?
Okay, it depends on what band the cell phone's operating in. It's either Cassiopeia A, a big supernova remnant, or Sagittarius A at the galactic center. And it depends on whether you're down at 1 gigahertz or up at higher, about down at 400 megahertz or up at higher frequencies for the cell phones.
The VLA Observatory is not that far from a public highway. What about truckers and city radios?
Yeah. What about it? It's a problem. In fact, let me tell you a story. The first SETI observing I ever did was at a telescope in West Virginia, Green Bank, West Virginia. Really hard to get to, really isolated, but the road goes by, and all of the telescope operators are also CB operators. So here's our experiment. Olden days, we had 2 tape recorders, and it ran through a big reel of tape in 3 minutes. Put on a tape before the source that we wanted to observe came overhead in the sky. Right? Take data when the source is not in the sky. Source is in the sky. Here's your second tape. Take data on the source while somebody else is putting a tape on here. And you ping pong. So our strategy was that we went back to NASA Ames, and I had a big grant from the guy who ran the center at the time to reduce the data. And so we didn't reduce any of the off-source data, the first tapes. We just reduced the data that had the targets in the sky. And if we found a signal, then we reduced the data that was off-source to see if there was a signal when the source wasn't in our field. And almost always it was. Here's one note. There was one special source that somebody else had looked at, and they thought they'd maybe seen something interesting. So every day I put that source in our observing file. We reduced the on-source tape. We saw a signal. Reduced the off-source tape. Didn't see a signal. Next day, reduced the on-source tape. There was a signal. Off-source tape. No signal. Third time we looked at it, and this probably went over about 5 days. Third time we looked at it. Yep, there is a signal there. But the on-source tape was kind of corrupted. The off-source tape, the one that I wanted to look at as a check, was corrupted. So, okay, the computer wizards at the computer said, well, we'll run this tape over a knife edge, right, and we'll clean it. Right. So finally, we got the on-source tape for the third day that we had looked at this source. And the signal was there. So what had happened? Well, you may know that there's a difference between civil time and sidereal time by about 4 minutes a day. And it takes, if you can imagine, the Earth going around the sun, and the sun is moving, and the Earth is rotating. So if you're looking at a point on the sky, right, it takes a different time than 24 hours by 4 minutes for you to come back and look at the same point in the sky. So this 4-minute difference was such that we were looking at the source just around 8 o'clock in the morning when shifts change. So for the first 2 days, the shift operator was still at the telescope when we took the first tape. But then as each day went on, it got later and later in the sky, or earlier and earlier in the sky, I'm sorry. And so by the third day, 8 o'clock in the morning, civil time, the operator was out of the telescope, out of the control tower, into his truck, off the base, and turned on a CD radio. And yet, that time, that earlier tape was captured, right, when, because of the sky changing, I was taking my on-source tape after 8 o'clock. And so the radio was turned on, where the other days I was taking my on-source tape before 8 o'clock. So we hadn't turned on a CB yet. All right, that was my first experience with false positives. And you can't imagine the excitement. We're sitting there at Ames. We're waiting. This could be it. Our first time out the door. This could be it. And then it didn't turn out that way. All right, overflow room. Is there anything I can talk about for you? Okay, I think we'll go on. Let's let's talk about what do we do when we get a signal, okay? First of all, you're excited as you can't believe. All right, but then what do? We actually do play this game, Make Me a Liar. So that did actually quite a great job of talking about what we would do to try and verify that a signal is what we think it is. So you start with your observatory and all the equipment that you have there, and you try and make sure that there isn't anything wrong in your hardware. So she kept pulling in everything, and she said, let's see if the FUD can see it. Well, that is actually something that we invented for SETI observing as part of the NASA project after we started observing with a single dish at Arecibo. And we found that the interfering signals, our own technology, is so time variable on every time scale that you can imagine that trying to hear a signal, then move off to see if the signal went away, and then come back on, you get totally confused by the fact that the signal itself is turning on and off. And so we said, well, one telescope is not enough. It's really difficult to get full time on multiple telescopes and to build the full signal detection gear that you need to do a search at both telescopes. And so we developed what we called a pseudo interferometer, all right? Which is that we got two telescopes and we had our full detection system on the bigger of the two telescopes. And we had what we called a follow-up detection device, a FUD, at the second smaller telescope. And like I have the situation at Green Bank when we started, when we had two tapes and I did an off-source tape before I did the on-source tape, what we do is we look at the same time at the same signal from both telescopes. But I don't worry about the second telescope until I have a signal that I'm really interested in on the first telescope. So the second telescope's data gets held for a short period of time in storage. And then when there's something to follow up on, I can look at the second telescope and I know exactly what I'm looking for, exactly where in frequency and time. And more than that, because we look for signals that are narrow band or pulses, rather frequency limited pulses, then if the signal is really coming from a distant point on the sky, it's going to arrive at the two telescopes, which are always separated by several hundred miles at least. It's going to arrive at a slightly different time at this telescope and a slightly different time at that telescope. Right? Same signal, but they're far away from each other on a curved Earth. And furthermore, that Earth is rotating. And so the instantaneous velocity of the first telescope and its product with the direction on the sky, and the instantaneous velocity with the second telescope and the direction that it sees the source on the sky are different, which means that the signal is not only going to arrive at slightly different times, but at slightly different frequencies at the two telescopes. And this is a characteristic that we can compute. So if the signal's really coming from that star, we know what the differential Doppler characteristics of the signal should be, and we ought to be able to see it in both telescopes and look for that characteristic signature. And if we don't see it, then it isn't really coming from the star. So that was our follow-up detection device. So she kissed the screen and said, "Thank you, Elmer," because Elmer confirmed that it saw the signal with the right differential Doppler. Now, you don't need that at the VLA. You don't need a pseudo-interferometer. You've already got an interferometer. That is what the VLA is, and this was not in the movie Contact, was not being used with all 27 telescopes phased up and looking at the same target. But nevertheless, There's enough information across the distances in that interferometer to have done that same trick without a follow-up device. But anyway, that was the first thing. You do everything you can at one site. And then you are really, really worried about a deliberate hoax. So you want to get an independent confirmation. You want to get a telescope to the west of you, because unless the source happens to be high enough in the sky near the North Pole so that it's always up, it's circumpolar, this source is going to set at your site. So you want to go west, right, where they will still be able to see it. And you want to ask them with equipment that you didn't build and software you didn't write. And once you can tell them exactly what to look for, they don't need this honking big signal detection system that we've built. You tell them what to look for, they can probably find it with a spectrum analyzer. And so that's what they did. They called up Australia, admittedly quite a bit west of the VLA, but there aren't many telescopes in between. And Ian said, yes, right, we got it, etc. They saw it. Then she asked him, well, what's the position? And that's a little crazy, because Ian is at Parkes, a 64-meter telescope. Pretty good, right? Big telescope. But the VLA is an interferometer spread over 13 kilometers. Its spatial resolution, its ability to pinpoint the source, is far superior to the 64 meters. So once he said Vega, she didn't actually have to ask them for the spatial accuracy. She already had it. But they did the right thing. Okay, and now, what are you going to do? Well, if you're part of the SETI Institute in our project, and most of the SETI, in fact, all of the SETI projects I'm aware of, you are going to tell the world, because this information is properly the property of all humankind. It doesn't belong to California or the United States. That signal's coming to the planet. The planet deserves to know about it and decide what to do about it. So, tell everybody is exactly the right answer. That whole sequence, as opposed to playing out in a few minutes on the screen, is probably going to take better part of a week in reality. And the big question is whether we can keep it a secret for that long to get through this process, or whether it will leak and then we'll have to deal with the world anyway. But that's our plan. That's our post-detection protocol. Verify, check it out at your own, in your own observatory, verify, get an independent validation, and then tell the world. So any questions about that? Yeah, here. Yeah, we'll wait for the mic. Come on down.
I'm just a lay person, but I'm going to ask this question from the sound of the actual signal caught me when I first heard it, thinking that doesn't sound like a sound I would think I'd hear from space. If I was the United States or America or the world transmitting a signal out, I think I would be sending out a single frequency pitched sound, whereas the sound that was coming in sounded like some tin can going down the street with bad joints. And so I'm asking, the question is that the sound with distortion of maybe a single pitch that was coming from a long distance, and that's what it went through as it got here? Is that what would have happened? Or did they just choose something that was entertaining?
It's another bit of artistic license, but it has to do with the fact that the signal was not continuous. To get the single tone that you want, signal has to be continuous. Once you make something a pulse, you broaden it out, and therefore it has more frequency components. And therefore, depending on how you want to sonify or shift the radio spectrum down into audible frequency ranges, you'll hear different things. So that there is a translation between the radio frequencies and audio frequencies. How you do that translation will depend on how beautiful it sounds or not. But now the single pitch would be a continuous tone, and they chose to do a pulse so they could demonstrate the prime numbers.
You have hundreds of artificial satellites passing over at any, through the day. Do you look in between passes? Do you filter out the signals from satellites? How do you count for it?
Dealing with our own technology is our biggest challenge. So discriminating between them and us is hard. A lot of things indicate to you that the signal is a satellite moving relative to the Earth. And so we look at all those characteristics. We actually do track the signal and require, a low Earth satellite goes over through the beam very, very quickly. Right? It changes if it's the carrier that you're hearing as opposed to the modulated information. That carrier is changing its frequency like lightning, very quickly, much more rapidly than a signal coming from a star that is changed by the rotation of the Earth will happen. Yes, so satellites are a problem. When we have a signal that we're interested in, when the system has automatically found a signal that it's interested in, at our project, what we do is an immediate follow-up. We don't wait till next week, right? We don't record it and then go back some later time. We follow up immediately. And in doing that, a satellite in low Earth orbit's no longer going to be there, right? We will not we will not reacquire it. Something in geosynchronous orbit, we would. And we end up building up a database of known interference that we check a newly detected signal against. And if it's something we've already seen, we don't continue to follow up on it. But we use this near real-time follow-up to help us discriminate against our own technology. Okay, there's one there and there's one over here.
I think you may have answered my question. It was about whether the geosynchronous GPS and now the ground stations, which you're using, and they use an L1 and an L2 frequency to try to determine what the atmospheric effect on time and frequency, or do you use similar techniques?
Well, first of all, we are pretty much shut out of the absolute bands of the GPS. We really, they're so strong and they're everywhere. We really can't observe through those. And in terms of the atmospherics, a single tone is shifted in frequency, but unless it's coming through the atmosphere of the sun, the solar wind, the very high velocity particles being ejected by the solar wind, that single tone does not get modified very much. So we avoid looking near the sun so that the signal doesn't get spread out. And the kind of thing we're looking for is so simple that it doesn't suffer much from scattering and absorption. So we can usually ignore the atmospheric effects. We do. Yeah.
In the movie, they were showing the prime numbers being received from Earth to the degree we're sending out a signal to let someone know there's intelligent life on Earth. What kind of signals are we sending out? Well,
We are actually not deliberately transmitting in an active mode in any way. Right? There have been a couple of stunts, but we don't transmit. The question is, should we? It's been said if everybody's listening and nobody's broadcasting, this stuff isn't going to work, right? And another take on it is, well, you know, we're expecting them to deliberately broadcast. We should do the same. That's a really loaded question, and there's a lot of angst and fear and emotions behind that question. And it's certainly not one that we as scientists think that we should decide for the planet. We're going to do it. So as a matter of fact, this discussion is bubbling up. It's very active right now. So the American Association for the Advancement of Science, the AAAS, is meeting in San Jose, California in February 13th, Friday the 13th. We have a session there to discuss, is it time to actively begin transmitting to the cosmos? So we have folks there who will be a pro and con on that sides of that argument. We have scientists and we have policy people that are going to participate. And the next day, Valentine's Day, we'll have a day-long meeting at the SETI Institute, a workshop to continue this discussion and to hopefully, so I'm having it in the Silicon Valley, because what I want to do is to get our Silicon Valley neighbors, tech folks who really are savvy about social media, to help us figure out how to have a conversation over the next year that is truly global, that includes traditions and religions and cultures that haven't been at the table before now. Because this really is a global question. Should we transmit? If so, what should we say? Right? And who's going to pay for it? Right? Kind of thing. And you know, I want to have a good global discussion. And since this phone technology is first adopted by every developing nation, I think we can. I think if the app doesn't exist for letting us cultivate that discussion, it should, because there are many conversations that we should have globally that have to do with the challenges that don't respect national boundaries that we're all going to have to deal with. So this is my hope for taking this conversation to the next level.
So there's many opinions on that issue.
You betcha.
Can you tell us what yours is about transmitting?
About transmitting? I think that we're not old enough yet. Okay? Transmission is a long-term strategy. Doesn't do a lot of good to yell for a minute or an hour or a day, because that signal is going to go past your intended receiver, and the chances that they're going to be looking at you in just that minute or hour or day are really small. Transmission is a long-term strategy. And you know, right now, we humans aren't real good at finishing 2-year plans. This could be a 10,000-year plan. I don't think yet. I think we should discuss it. I really think it's timely to discuss it because it may actually help to bring people around the globe together. And again, we have so many immediate challenges that need global thinking, right? That maybe this is a start of that. So I don't think we've grown up yet enough. But if we are able to survive into the future, to become a long-term, an old age technology, I think transmission's in our future. Okay. Unless there are questions in the overflow room, I think I'm going to go move on. Because you were right. It's hard to get through many clips. All right. So here's a little tidbit for your next cocktail party conversation. In August of 1996, NASA JSC scientist handed Robert Zemeckis, the director of this film, a huge present. All right. Is he talking about the detection of a signal? He's talking about the claim that Allen Hill's 84001, a meteorite that we're pretty sure came from Mars and was kicked off Mars at the time when Mars was wetter and warmer billions of years ago. The claim by scientists from Johnson Space Flight Center, published in Science, that meteorite contained structures that were best explained as biological rather than geological. huge, big excitement in the science community, reached up to the president's level. And up until August of 1996, Morgan Freeman was under contract to play the president. But Zemeckis loves this stuff. He loves to cut in real into fictional. So I don't know how much they had to pay off Morgan, but he told me once he was disappointed that he didn't get to play the president. Anyway, this was super. This is great. If you look, you see the sun. The press conference took place outside, actually. See the sun glinting on his hair, and there are a few little strands that wiggle in the breeze. But this was great. Any questions? Okay, over here.
Did they ever resolve definitively whether or not those were, in fact, microscopic fossils? I had heard that they weren't, but I wasn't sure if they'd finally put it to rest.
You know, Gibson or McKay over at JSC standing by their story. The rest of the scientific community pretty much has been able to show they can reproduce that with geological processes. But the thing that did, that meteorite and the claim, it gave us incredible new instrumentation with which to look at nanograms of material. It just really drove the technology development ahead hugely. So it's a great boon to the sciences. All right, let's see what else I wanted to tell you. Oh, well, let's talk about Einstein. Okay, so before she goes, we're thinking in terms of special relativity and time dilation, right? And the fact that time will run slower for the occupant moving at the speed of light than it will for the folks left at home. So as in Interstellar, you expect someone who goes out, comes back, to come back to a world where there's been a lot more aging than the traveler has experienced. By the time you get to what actually happened and the wormhole transportation, you're not now talking about special relativity, you're talking about general relativity. You're talking about time travel in addition to space travel through the wormhole. And so the transit system whisked her away and brought her back in space and exactly or almost exactly the same instant in time. So these were two really very difficult concepts that I think the movie portrayed extremely well. So I just wanted to make the special relativity, general relativity comparison, because maybe you didn't get that. And also the filmmakers were very clever. They were very, very good here. Questions? All right. Or maybe Carl was clever, yes. And then there's one over there, too.
You mentioned a blind colleague. Was this someone who was, actively working as you were
Yes.
on your work?
Yes. In the book, there's no blind physicist. But in 1995, when we were working at Parkes Observatory in New South Wales, it wasn't Warner Brothers. Someone else had the rights to Contact, and they were planning on making it. The director was the man who did Lorenzo's Oil, and I'm sorry, I don't remember his name. But Uma Thurman was signed to play the Ellie Arroway character. And they were Sydney-based, and we were at Parkes. So they were going to come out. They came out to the telescope to get look and feel. And it turns out that my colleague, Kent Cullers, who helped write all of the signal detection algorithms, helped us develop the FUD, is a blind physicist, been blind since birth. And Kent likes to point out that no-sighted astronomers any better than he is because the data rate is so enormous. It's machines that have to do it, and he's good at talking to machines. So they came to Parkes, and unfortunately Uma Thurman didn't come at the last minute, and so my male colleagues were so disappointed, right? Their tongues were hanging out thinking of this fantastic movie star showing up. But Kent was there, and the director thought that was amazing. And so it's at that point that the blind physicist got written into the story. And as Kent left Australia, he stopped by Sydney to screen test to see if he could play himself. And they decided that on a good day, yeah, probably he could, but the part expanded as it kept getting written, and so they got an extremely good actor to do it. All right, you had a question. Yes. Then wait for the mic.
If you'd been in Jodie Foster's position, would you have gone?
Absolutely. In a heartbeat. In a heartbeat. I want to go. So, this whole thing, actually, what's the value? What's the value of all of this? Why would she go? Right? I think it all revolves around this one question. That's it. That's why SETI is important today, even more than ever before. We're looking at a future. So many ways it could end badly. If we are able to detect a signal from a distant technology, statistically, hands-on, they're going to be far older than we are. Can't be any younger, can't be any less advanced, because they wouldn't have any technology to play the game, right? If we detect a signal, it's going to be from an older, more advanced technology. Therefore, we get an instant proof of the fact that it's possible to survive to be an old technology. We know instantly that on average, the longevity of a technological civilization is great, much greater than the hundreds of years that we can claim. And to me, knowing that existence proof is so key. It is so motivational. It doesn't solve our problems. It is an extraterrestrial salvation, right? But it tells us that somebody else made it through. Therefore, if we work hard enough, we can too. And I think that's the message that it's so lacking today, and it would be enormously empowering. So I think that's why SETI matters. Questions? Yeah. Wait for the microphone.
I'm concerned you might be overlooking a key point. They are. I'm concerned about a point might be overlooking. They are an older civilization and I would agree with what you said, except for one thing. We are not in the same time that they were in before, okay? And so that's a tremendous potential difference in their experience and what it carries over for our future experience.
Okay. I think that what you're trying to say is that we might get a signal, they might no longer be there. They might have done themselves in. Is that correct?
No, they may still be there, but their past was far before our past.
I think that our greatest threats are not environmental on the largest scale. Yes, we do need to take care of those nasty rocks that have our name on it, right, coming in from space. We have to learn how to deflect threatening asteroids. But in order to have the technology that can transmit this signal, they've had to go through some sort of technological development. What she refers to is the technological adolescence, where we find ourselves with technology to do both good and technology that has been thoughtlessly used and is causing a great deal of challenge and threat. So they made it through this bottleneck. All I'm saying, it's a proof of concept that we can too. Way in the back. And then over there in the middle.
As a kind of a follow-up to that, Carl Sagan also warned our people about nuclear winter and the use of nuclear warheads and that kind of thing. If that were to happen to the Earth, would it leave an environmental situation that could be detected from a long distance away? In other words, if we were looking at other planets at a point where we can see their atmospheres or see evidence of things in their atmosphere, would we be able to tell that a civilization had blown itself up?
What is the long-term signature of a nuclear annihilation? It isn't actually very long-term. People have looked at that. There are all kinds of assumptions that you can make, but probably not. That probably would not mark us. It wouldn't have put a positive marker. It wouldn't add something to the atmosphere for a long enough time that you're likely to say, oh, that planet, they did themselves in. But what it would do is eliminate markers that are there now. The biosignatures in our atmosphere due to the incredible biology on the surface of the planet. It might eliminate some of those if it were significant enough to do in the large-scale photosynthesizers. But even there, the greatest concentration of them are the small microorganisms in the ocean. They might survive. So that isn't, first of all, it isn't a hopeful thing to go looking for, so nobody's built an instrument that's optimized for that. Secondly, it probably doesn't mark the atmosphere for long enough to serve as a good marker. There was a question there in the middle.
I think you're wonderful.
I have a great script. I have a fabulous script.
Now tell me something. Jodie Foster, she did not believe in God. Do you?
Okay, in that movie, Jodie Foster does not believe in God. I don't know what Jodie Foster, the actor, actually thinks. All right. I have the same approach that character does. I think the universe is awesome. I am so in awe. On the other hand, I'm also really impressed by how these bits of stardust, that's what we are, have been able to puzzle out how it works, maybe. We got back to the Planck time, 10 to the minus 37 seconds after the beginning, and our physics goes to hell. We can't make gravity and the strong forces play together. But that's a challenge. It isn't a fundamental. I'm not yet persuaded to say, okay, for this, you need an all-powerful creator being to make it happen. So the universe is wonderful. It's fabulous. However it got here, I am just delighted to study it. Okay.
I've given this a lot of thought, so I can make it really long, but I'm going to deliberately keep it really short. Anyone that can communicate over those kinds of distances can only be able to do so if they have learned to work together.
Amen.
Rather than what we're doing right now is splitting ourselves apart by petty differences.
I think you got it. Thank you. That's what SETI is all about. I love to tell audiences that if you think, you've spent an hour now with me, hour and 15 minutes, maybe you've been thinking a little differently than you did when you walked in the room. Maybe we've been able to push your perspectives out, give you a more cosmic perspective. Think about it. Think about it. From the distance of another civilization, we're all the same. We're all Earthlings. And so I think the whole concept of working together on SETI as a global endeavor has to have the effect of diminishing, trivializing the differences among humans that we're willing to shed blood over. So SETI's good. Yes.
Doctor, the movie talks about recognizing a signal in pretty much instantly, and you described it as taking maybe a week to verify a signal. I've been running SETI at home for more generations of computers than I could count. So what have my computers been looking for all these years?
Oh, they've been looking, actually, your computers are using the same signal detection algorithms that we use in near real time. Okay? And so they've been looking for the same sorts of signals. On the other hand, the detection doesn't happen in your computer. The recognition of something happens in your computer, and then it goes to Berkeley. And there it's added to all the other signals that have been found. And what is required for detection is that the next time the telescope passes over that same position on the sky, listening at the same frequency, that the signal be seen again. And twice isn't enough. Again, we're working with so many experiments here, so many tests that are done, that it isn't until you get 5 or 6 detections of the same thing from the same place on the sky that is statistically significant, that the Poisson statistics say, hey, that's probably not noise. So Berkeley is accumulating all of the results from your computer and everybody else's computer, and it's building up these candidates for signals and making a prioritized list of things that look more and more statistically likely to be something other than noise. And once a year or so, they get some discretionary time from the director, and they take their list and they go back and they take control of the telescope and they look to try and find these signals again. So far, it hasn't worked. Now, if they found the same signal 5, 6, 7 times before, then this isn't such a strange, this isn't such an unreasonable approach that they should expect when they go back and look again, if it's really what they think it is, that they should find it again. So far, it hasn't worked. But SETI at home is great. It put distributed computing on the map. It's fantastic.
You made the comment that you thought that if we heard another civilization, it would be much more advanced than ours. Here on Earth, our history has not gone very well for the less advanced civilizations when they make contact. Any comments?
Well, that's the heart of this debate about active SETI. You know, if you're in the jungle, don't shout because the tigers will come and eat you up at night. When you try and argue from analogy of the contact of more advanced and less advanced civilizations on this planet, you have to understand that the biggest factor in that contact was a germ vector, was disease, was microorganisms that could be transferred from one group to another that had no resistance to it. Less likely to happen by remote communication. But still, that's part of the argument behind active SETI and why it should be a global discussion. Okay, there's one there and there's one there.
We should take one more here and check with the overflow, and then we'll do one more clip.
Okay.
Is there an overlap between the SETI community and the Kepler community where you're looking in the regions where the Goldilocks planets are?
You betcha. Okay. Since 2011, January, when Kepler made its first announcement of exoplanet candidates, that is where we point our telescope. So we use the Allen telescope array every day. We form 3 beams on the sky. Those 3 beams are pointed at 3 different exoplanet systems, both from the Kepler field and, when that's not up in the air, the ground-based detections through radio velocity. So we're looking at exoplanets. We have been since 2011. What have we learned since 2011? We've learned that probably every star has planets. And so now we're wondering whether we should switch a strategy to looking to the nearest stars where we can hear the faintest signals, because we have a pretty good idea that they're going to have planets too. Okay, overflow room, are you all asleep? Yeah. They're taking the popcorn. All right. All right, let's see if we can get another clip in. Okay, the setup. All right, this is the ending of the movie. Zemeckis changed it from the ending of the book. He was going to change it anyway because the idea was that the book ended with this, a circle being formed in the digits of pi that was too esoteric for the general public, right? Carl thought better of us than that. But how did he change it? He changed it to set up a sequel. Right? You got this 18 hours, you got new telescopes. It begs a sequel, but apparently it's not going to happen because the movie didn't make enough money. That's what I've been told. All right, so I think there's one more clip I want to show you. On the other hand, if you have screenwriting skills, come talk to me about let's tell a story. Okay, this is what absolutely did me in at the premiere, right? We were looking forward to seeing the credits and all of this setting. This did me in. Unfortunately, Carl died while the film was being edited, and we lost him. But this film is a great tribute to him, and I hope you've enjoyed it as much as I have. Thank you.